I am Benjamin Epp, and my partner is Austin Hall. We are Group 4. We're doing a report on assignment number 9, which is machine vision and process monitoring of 3D printed projects. The first part of assignment 9 was image acquisition and manipulation. This was to simulate um, how you would go about capturing images as you did a 3D print of an object. The first thing that we did was we remoted into the Raspberry Pi device and obtained an image that can be seen there on the left with the cage, the star, and the ruler. From there, we imported into Google Colab and cropped out the green cage. Now, after the green cage was cropped out, we converted that color picture into grayscale, and then from grayscale we converted it into a negative of that. And basically what that did was converted it so that the part is now black and the background is now white. So therefore we take that, at the same time we did the same process, we cropped, grayscale, and then took the negative of the standard image that was given to us, and we overlaid the two images to see what the differences between the two images are. And this is kind of shows that if you have a standard of what this a good part should look like as is being 3D printed, and then as you're doing any new parts, you're comparing that against that standard image to see if you have any shifts from the current part to the standard. Now, since these images are inside Python or inside Colab, basically we're able to do a lot of other things more than just looking at the image and comparing the image. It takes that image and breaks it up into a bunch of matrices. And from that, you're able to obtain a lot of information. One of them is you're able to obtain how many black pixels were in the picture. I ran a couple different codes, and the total number of black pixels that was ever came back per the Python code was 1. But more than that, we're able to run some descriptive statistics as well, mean, variance, all the quadrants, as well as the skewness and kurtosis. As well as we took that data and were able to plot a histogram. So you're able to use all this information just from an image that's converted into matrices, basically from pixel values, and you're able to create either a standard or you're able to compare that picture to a standard. And so if anything goes awry, you're able to track it, especially in a control chart.
The next stage of the project was to identify our process by which we would evaluate the data given. As part of the project, we were given a spreadsheet with data that told us for 17 different parts how they compared to a golden standard project or part across 243 different printing layers. At each layer, the parts were measured in terms of the number of pixels different from that golden standard part. The problem is this data, while very thorough, creates a situation where each layer is not going to have the same number of pixels to compare, and therefore the data is not necessarily one-to-one. So the best way to get over this is to normalize the data. The way we normalized the data was we took each pixel difference value, we subtracted it by the mean for that specific layer, and then divided it by the sample standard deviation in order to make sure that each layer would have a mean of 0 and standard deviation of 1, and then we could treat each layer as a quality characteristic to plug into our chart. Then we had to check for correlation, which will be shown on the next slide. We developed a control chart with the phase 1 data to determine the upper and lower control limits. Then we plotted the phase 2 data in the control chart, which allowed us to determine the in and out of control data points and parts, and ultimately draw our conclusions. As mentioned in the previous section, the next step after normalizing the data, which can be seen in the attached Excel file, was to develop some sort of chart that would help us determine if the data was truly independent. In order to do this, we developed ACF charts, or autocorrelation function charts, to compare the data for the 3 different layers that were required as part of the project. That was layers 100, 173, and 200. And as can be seen in the PowerPoint slide we're on, all 3 autocorrelation functions indicate that their data was in fact independent. Once we knew that the data was independent from the ACF charts and identically distributed, which we knew from normalizing the data was going to be the case, we were able to plot this data on a MEWMA chart, which is the chart that we chose to use for our multivariate analysis. As mentioned earlier, we use the quality characteristic of layers, making each layer its own quality characteristic, and for the 3 layers chosen, 100, 173, and 200, each of those were determined to be a quality characteristic that were rolled up into a control chart, such as this one, that could identify and evaluate multivariate scenarios. This was done and developed for the first 10 parts, and that was considered our phase 1 data in order to establish our upper control and lower control limits, as well as establish the different parameters by which we would evaluate the chart. After the control chart was set up with the phase 1 data, it was time to plug in the phase 2 data and determine which of these parts were out of control. What can be seen is that part 16, which is indicated as part 0 in the top chart, is in control. However, all of the other parts, including part 23 as requested in the project, they are all out of control based on this control chart. What can be seen is that at a point, all of the parts start to become out of control. And so what I would recommend as part of this process and evaluation is when stuff like this happens, to have some sort of a trigger point that causes the system to stop and to be reevaluated, because more than likely it's a calibration issue or something got off in printing and it's causing all of the data to be completely skewed one way or another. And if reset, it could possibly get things back on track and under control.